Defect inspection in semiconductor industry. Defect inspection plays a critical role in ensuring the quality and reliability of semiconductor devices throughout chip manufacturing. As device features shrink and complexity increases, detecting and analyzing even the smallest defects becomes essential. The process begins with detection, using advanced inspection tools to identify anomalies on wafers, including particles, pattern defects, and surface contamination. These tools include optical, E-beam, and other high-resolution techniques capable of spotting nanoscale issues. Next is analysis, which focuses on identifying the root causes of defects. By classifying and tracing them back to specific process steps, manufacturers can uncover patterns or systemic issues. This analysis is crucial for driving continuous improvement. Finally, prevention involves using insights from detection and analysis to implement corrective actions. This helps improve process stability, reduce scrap rates, and increase yield, making defect inspection a cornerstone of semiconductor manufacturing excellence. Inspection process workflow. The inspection process workflow outlines an end-to-end pipeline for quality control in semiconductor manufacturing. It begins with wafer prep, where wafers are loaded and aligned, environmental conditions are stabilized, and the correct recipe is selected to ensure consistency. Next is data collection, involving image acquisition, multispectral scanning, and sensor data capture to collect detailed inspection data. In the AI processing stage, this data undergoes image enhancement, pattern recognition, and feature extraction using advanced algorithms. Defect detection then identifies anomalies by performing threshold analysis and mapping their exact locations. In the classification step, defects are categorized based on type, severity is assessed, and priorities are ranked accordingly. The root cause stage follows, using trend analysis, correlation mapping, and process tracing to determine why the defect occurred. In the decision phase, pass-fail criteria are applied, recommendations are made, and quality metrics are evaluated. Finally, reporting ensures data is logged, reports are generated, and insights are cycled back through a feedback loop to improve upstream processes. Inspection process workflow, metrics, and data flow. This view of the inspection process focuses on performance metrics, timing, and data handling, key indicators of system efficiency. Process timing is remarkably fast. Data collection typically takes just 2 to 5 seconds, while AI processing completes in 0.5 to 2 seconds. Analysis and decision-making follow quickly within 1 to 3 seconds. Altogether, the total cycle time for a full inspection is only 4 to 10 seconds, demonstrating the power of advanced automation. Quality metrics are equally impressive. Inspection systems achieve 99.8% accuracy in identifying defects, while false positives are kept extremely low at just 0.02%. Repeatability, a critical measure in manufacturing, stands at 99.5%, ensuring consistent results. These systems also support 24/7 uptime, enabling round-the-clock operations without downtime. Finally, the data flow includes 3 essential components: high-resolution wafer images, metadata containing process parameters, and analytics that track machine learning predictions and trend data. Together, these ensure comprehensive, real-time insight into quality control and continuous improvement. Industry impact and trends. The semiconductor inspection industry is experiencing rapid and transformative growth. By 2026, the market size is projected to reach $15.9 billion, representing a 44% increase from 2024. This surge is driven by multiple converging factors, including the rising complexity of semiconductor devices and the need for higher yield. From 2024 to 2032, the industry is expected to maintain an annual growth rate of 8.5%, signaling strong momentum across the value chain. Leading semiconductor fabs have already embraced AI with a 75% adoption rate, using it to drive faster, smarter inspection and defect classification. This technological leap is also improving yield, with advanced inspection contributing to a 15% increase. The market growth chart reflects this upward trajectory, with a steady climb from $7 billion in 2020 to over $20 billion projected by 2028. Meanwhile, the donut chart shows AI, ML, and E-beam inspection leading in technology adoption, followed by traditional optical systems, X-ray, CT, and emerging tech. Industry impact and trends, market growth, technology adoption, and future outlook. Several major market drivers are fueling the inspection technology industry. First, the expansion of 5G and the Internet of Things is increasing demand for advanced chips that require more rigorous inspection. AI and machine learning processing further drive the need for specialized processors, which must be defect-free to ensure performance. Automotive electronics, especially in electric and autonomous vehicles, are pushing for higher reliability through advanced inspection. Miniaturization is another key driver. Smaller node sizes demand more precise detection of microscopic defects. Regionally, Asia-Pacific dominates with 52% of the market, followed by North America at 28% and Europe at 15%. Notably, Taiwan, South Korea, and China together account for 40% of global demand. Looking ahead to 2025-2030, emerging trends include quantum sensing, edge AI, and cloud-based analytics. Investment will exceed $50 billion in fabs, with heavy focus on R&D and strategic alliances. However, challenges remain, including sub-3 nanometer complexity, skilled labor shortages, and balancing performance with cost. Conclusion and future outlook, shaping tomorrow's semiconductor quality assurance. Defect inspection is no longer optional. It is critical for success in semiconductor manufacturing. As devices shrink and complexity rises, identifying and addressing defects early becomes essential to maintain both yield and quality. This need is driving rapid evolution in inspection methods. Artificial intelligence and machine learning are playing a transformative role, offering intelligent automation and real-time analytics that vastly improve speed, accuracy, and decision-making. The future is clearly multimodal. Optical, E-beam, and X-ray technologies are being combined to create powerful inspection systems that can detect a wide range of defect types across different layers and materials. This integrated approach ensures higher reliability and process control. All of these factors are contributing to massive growth in the industry. By 2026, the market is projected to reach $15.9 billion, supported by an annual growth rate of 8.5%, highlighting a future rich in opportunity and innovation. Conclusion and future outlook, future technologies. Looking ahead, the semiconductor inspection landscape is being shaped by a suite of next-generation methods and transformative goals. Edge AI processing enables real-time defect detection with sub-second response times, which is crucial for maintaining throughput and reducing delays. Quantum sensing offers ultra-precise measurements at the atomic level, pushing the boundaries of what can be detected. 3D reconstruction is becoming vital for comprehensive wafer topology analysis, helping manufacturers visualize structural variations in detail. Digital twin integration allows for virtual physical process modeling, giving engineers the power to simulate and optimize processes before real-world implementation. On the transformation front, smart manufacturing is advancing toward autonomous fabs with self-optimizing inspection systems. Predictive quality uses AI forecasting to prevent defects before they happen. The industry is also striving for zero-defect goals, aiming for 99.9% yield in advanced nodes. Finally, sustainable production is being prioritized, with defect prevention playing a key role in reducing material waste and energy consumption. Conclusion and future outlook. The future is now. Defect inspection technology is no longer just a supporting function. It is the cornerstone of semiconductor excellence. As the world increasingly relies on high-performance, reliable electronics, the ability to detect and eliminate defects early in the process becomes a vital competitive advantage. To shape this future, the industry must take deliberate action. First, it must invest in advanced inspection technologies, capable of keeping pace with rapidly shrinking nodes, and increasing complexity. Second, it must innovate using AI-powered solutions that bring intelligence, speed, and adaptability into the inspection process. Third, successful integration of multimodal inspection systems, combining optical, E-beam, and X-ray tools, is critical for comprehensive coverage across all layers and materials. Together, these actions elevate quality from a one-time goal to a continuous habit. As the quote says, "Quality is not an act, it is a habit." Excellence in inspection is the foundation for sustained innovation and technological progress worldwide.